G stands for the state function or the Gibbs function. It does not depend upon the path of the processes. Change in the enthalpy. Then delta G values are also become positive, and it is a not spontaneous process and is a non-spontaneous process. Change in the Gibbs free energy, which able to predict the feasibility of the process or the spontaneity of the process at constant pressure as well as at constant temperature. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the thermodynamics. Under this unit, we have discussed about the spontaneous and non-spontaneous processes, and also we have understood about the topic of entropy and how does the entropy cannot able to predict the spontaneity of the reaction, and how does the enthalpy also cannot able to predict the spontaneity of the reactions we have understood. Today we are going to understand one more different topic, that is Gibbs free energy. In addition to that, we are also going to understand the predicting the feasibility of the process by using Gibbs equation, and effect of temperature on the spontaneity of the reactions we are going to understand, and the relationship between the standard free energy and the equilibrium constant we are also going to understand, and lastly we are going to solve the sum of the numerical based upon the Gibbs free energy. First, we will say Gibbs free energy. So, already in our last session, we have understood that enthalpy as well as the entropy cannot able to predict the spontaneity of the particular reaction. That is why, in chemistry, they have introduced a new terminology, that is Gibbs free energy or the Gibbs function. So, this was given by Gibbs. Okay. The Gibbs free energy is the maximum amount of energy which is available for the system during the processes, and that can be converted into useful work between the initial as well as with the equilibrium state. According to the Gibbs free energy, we have a relationship, that is G is equal to H minus Ts. Remember, T is a temperature constant and H is a enthalpy, S is a entropy. So, you can say that the Gibbs free energy is related to enthalpy as well as with the entropy. So, it is the maximum energy available for the system during the reactions or during the processes. Hence, they have introduced this concept to find out the spontaneity of a reaction. So, this equations, which is also known as what? Gibbs free energy equation. G stands for the state function or the Gibbs function. It does not depend upon the path of the processes. And the change in a Gibbs free energy is also obtained by delta G is equal to delta H minus T delta S. Remember, delta G is a change in Gibbs free energy and delta H is a change in the enthalpy, and T delta S, T is a temperature and delta S is a change in the entropy. So, this is how enthalpy as well as the entropy, they are linked with one another by using a new state function, that is a Gibbs free energy or the Gibbs function. These equations are also known as Gibbs free energy change equation. The above expression contains both the enthalpy factor as well as with the entropy factor. The change in the delta G alone can predict the spontaneity or the feasibility of the processes, and delta G gives a criteria for spontaneity at a constant pressure and a constant temperature. What is that relationship? That is, change in the Gibbs free energy is obtained by change in enthalpy minus change in the entropy. So, this change in the Gibbs free energy which able to predict the feasibility of the process or the spontaneity of the process at constant pressure as well as at constant temperature. You can see with that the values. If the delta G value is negative, then the reactions are said to be spontaneous. If the delta G values is negative, the reactions are said to be spontaneous. If the delta G values are positive, we say it is non-spontaneous processes. If the delta G values are equal to 0, then we say that system is at equilibrium. Like this, the spontaneity of the reactions can easily predict only by using a Gibbs free energy, not by using a entropy, either with the enthalpy also. This is how the Gibbs free energy, which has been linked with the enthalpy as well as with the entropy, and the change in the Gibbs free energy, which gives an idea about whether the reaction is spontaneous or non-spontaneous. Only when the delta G values are negative, it shows that it is a spontaneous process. If the delta G values are positive, it is a non-spontaneous. If it is equal to 0, it indicates that the system is at equilibrium state. Okay. How does this Gibbs free energy, which also able to predict the feasibility of the reactions, will understand now. Okay. The Gibbs equation is delta G is equal to delta H minus T delta S. The case 1 is I am taking the exothermic reaction. If I consider exothermic reaction, we know that the delta H values are become negative. So, if the reactions are said to be exothermic, the delta H values are become negative. If delta H values are become negative, the delta S values will be become positive. I am considering a condition where my reactions which is happening in the exothermic way, where the delta H values are negative. If delta S values are positive, what will happen to the delta G value? We'll see now. Okay. That is delta G is equal to delta H minus T delta S. Now, as I said, my delta H values are negative minus, okay, if the delta S values are positive, okay, positive, what will happen? So, you will get a minus into plus, it is a minus only. So, you will get a delta G values are negative. So, this indicates that if the delta G values are negative, we know that it is a spontaneous processes. Correct, no? So, it is a spontaneous process. If the temperature is lower than that of the delta T delta S, which is lesser than the delta H, the delta G values are become negative and the process are said to be spontaneous. If the temperature is high than that of the change in the enthalpy, then delta G values are also become positive and it is a not spontaneous process and it is a non-spontaneous process. Thus, an exothermic reaction which is not a spontaneous at a given temperature, maybe it becomes spontaneous at a lower temperature. Even the temperature will also affect here to predict the change in the Gibbs free energy. Remember, if the temperature is lower, then it indicates that the reactions are positive. If the change in the temperature is very high or the system which is having a very high temperature, then the reaction is not a spontaneous, it is a non-spontaneous. Hence, only at the lower temperature, we can say that the Gibbs free energy change will become negative so that the reactions are spontaneous. Okay. We'll take one more case where I am considering the endothermic reaction. Further, the delta H values are become positive. I am considering a delta S values are positive. What will happen to the equation now? That is delta G is equal to delta H minus T delta S. Correct, no? If it is a positive value minus if the delta S values are positive also, what will happen to the delta G values? It is also become positive. Then the reactions is said to be, it is a non-spontaneous process. But how does the temperature will affect here? We'll see now. If the temperature is lower than that of the T delta S, which is lesser than that of the change in enthalpy, the delta G values will become positive. If the temperature is higher, then the T delta S will become greater than the change in the enthalpy, then the delta G values will become negative. It is a spontaneous processes. Okay. Thus, the endothermic processes which does not are spontaneous at a given temperature, but it can become a spontaneous at higher temperature. This is how the endothermic process which also get affected with the temperature only with the increase in a temperature or with the decreasing in temperature. So, If the delta S is negative, if you consider one more condition, what will happen to the change in the Gibbs free energy? It will become positive, and it indicates that it is a non-spontaneous processes. And finally, we can consider one more condition where the delta H, which is equal to T delta S, and a change in the Gibbs free energy will be equal to 0. This indicates that the system is at equilibrium state. So this is how, by understanding the endothermic, exothermic, and the system is at equilibrium condition, the Gibbs free energy will be get changed and gives a different values. Remember, it also affected towards the temperature. We can recall that the effect of temperature on the feasibility of the reactions, on the spontaneity of the reactions. Suppose if the delta H values are negative, I am considering a reactions where delta H is negative and delta S is positive. The change in the Gibbs free energy will become negative. This indicates that the reaction is spontaneous at all the temperature. Now, I will consider the reactions at lower temperature. Okay, these are all exothermic. Okay. When during the exothermic condition, we know that the delta H is negative, delta S I will consider as a negative also. The change in Gibbs free energy will become negative at lower temperature. This indicates that the reaction is spontaneous at a lower temperature, we can say. Suppose if you consider delta S is negative, then if you increase the temperature at very high temperature, you can say that delta G values are become positive. We can say that the reactions are become spontaneous at higher temperature. Like this, the temperature which is also affecting to the spontaneity of the reactions with the Gibbs free energy can also be understood. We have one more reaction, that is endothermic. Okay, we know that in the endothermic reaction, delta H will become positive. I am considering a condition when delta S is positive, at very high temperature the reactions is spontaneous at a lower temperature. If delta S is positive, then very high temperature, the change in the Gibbs free energy will become negative, and it indicates that the reaction is spontaneous at very high temperature. Now, if you consider the delta S values are negative, at all the temperature, the delta G values which also become positive, this indicates that the reaction is also spontaneous at all the temperature. This is how, the effect of temperature on the spontaneity of the reactions can also be understood by using Gibbs free energy. Now, let us understand a free energy change or the Gibbs free energy that is indicated by delta G. And standard Gibbs free energy is denoted as delta G naught. How does it related to the equilibrium constant, that is Kp? We'll see now. Okay, I'll consider the reaction where A plus B is giving rise to C plus D. For this reaction, I'm going to write the change in a Gibbs free energy. The change in Gibbs free energy for this reaction can also be written as delta G is equal to delta G naught. This is the standard free energy change plus RT ln of a PC into PD divided by PA into PB, because these are the reactant, these are the product at a given temperature. Okay. Now at equilibrium, we know the delta G values are 0. Then the log of a PC into PD, that is a product divided by the change in the reactant, will be equal to Kp, because at equilibrium condition I have considered. Now what will happen? I am taking the delta G outside because the delta G will be equal to 0. I am taking the delta G naught outside, which will be equal to the minus RT into ln Kp. Okay. So, if you consider delta G will be equal to 0, then the whole thing will be equal to Kp. Now, I can rewrite the ln in terms of log. Delta G naught will be equal to minus 2.303 RT into log Kp. So, this is the final equations which we used during the calculations of standard free energy change, and it has been linked with the equilibrium constant, that is Kp. We'll see some of the numerical, then we'll understand how to solve with this standard free energy change. A partial pressure of the equilibrium constant of the reaction is 7.5 into 10 to the power of 3 at 298 Kelvin. Calculate the standard free energy change for this. So what is the formula? We have the standard free energy change is obtained by minus 2.303 RT log of Kp. Correct, no? So we know that they have given the temperature as well as the Kp value they have given, that is the equilibrium constant they have given. So what is the Kp value they have given? It is 7.5 into 10 to the power of 3, and temperature they have given, that is at 298 Kelvin, and R value which is also known, that is 8.314 joules per Kelvin per mole. Okay. Now if you substitute to the above equation, that is minus 2.303 into 8.314 into 298 into log of 7.5 into 10 to the power of 3. Okay. Now I'll solve the log here. A log of 7.5 into 10 to the power of 3 can be written as log of 7.5 plus log of 10 to the power of 3. Okay. Log of 7.5 plus 3 into log 10. Okay. So log 10 value is 1. We need to find out the log of 7.5, which is nothing but a 0.875 plus 3 you need to add. So if you add 3.751. Now you substitute to the above equation, minus 2.303 into 8.314 into 298 into 3.8751 minus 2211.3 joules per mole. If you wanted to convert in terms of kilojoules, you can rewrite it as minus 22.1103 kilojoules per. This is how we can easily solve with the 2-mark question based upon the standard free energy change. But while solving with the log values, be careful. First find out the log value, then add a remaining value, you will get a log Kp value. Okay. We'll solve one more numerical. Calculate the standard free energy change for the conversion of oxygen to ozone at 298 Kelvin if the Kp value for this conversion is 2.47 into 10 to the power of minus 29. So we have a relationship, that is delta G naught is equal to minus 2.303 T into log of Kp. Correct? So 2.303, R value is 8.314. What is the temperature they have given? 298 into log of, what is the Kp value they have given? 2.47 into 10 to the power of minus 29. So I'll solve the log value here. A log of 2.47 into 10 to the power of minus 29. I can rewrite this as log of 2.47 plus a log of 10 to the power of minus 27. So you need to find the log of 2.47 plus minus 29 into log 10. 0.392 plus into minus is minus 29. Minus 2.608. So now you substitute to the above equation, you will get minus 2.303 into 8.314 into 298 into minus of 2.8608. Okay. So how much you will get? Minus into minus, you will get the plus delta G values here. Okay. The standard free energy change will be plus 163,000 joules per mole, or you can write delta G naught will be equal to 163 directly kilojoules per mole. Okay. This is how, we can easily solve the numerical based upon the standard free energy change, which has been related to the equilibrium constant, that is Kp. Hope you all understood with the last session on the thermodynamics. I'll come back with the next unit. Till that, take care, be safe. Thank you.